Let's get started. In today's lecture, we're going to start talking about how to build a CPU. Hopefully this is an exciting topic, right, for most of you. And we're going to start with a simpler one, a basic one first, called a single cycle microprocessor. Right? First, a few announcements. Last time I talked about this bonus point, right? Although I sort of left undefined with the meaning of this bonus point. Really for bonus point, if you earn one, it's gonna give you one extra slip day, basically 24 hours, right, for any remaining assignments. Hopefully this is useful for many of you, right? Because I know that some of you are already asking about how many labs do we still have, right? And we do have quite a few, right, lab assignments. We are talking about lab 3, right? And there'll be lab 4. Lab 4 will have 3 parts. In case you want to know the detailed schedule, right? So everything is on the course website. Okay, we have 4 labs in total. And also we have 2 more homework. Okay, hopefully this extra slip day will be helpful, right, for some of you. There are 2 ways to earn this extra slip day. Okay, first, we already practiced a bit, right, in the last lecture. You can try to answer this bonus question during the lectures, and there'll be one today as well. Although I understand that many of you may not be lucky enough, right, to be the first to answer that question. And here's the second way to earn this bonus point. You can also watch this recorded Verilog tutorial and give us a short review, right? So you can just, when you request for the slip day, all you need to do is, first, if you want to get the extra slip day, right? All you need to do is, when you want to request the slip day, just email us, right? And then write down a few things, right? What are the things that you like about this tutorial, and what are the things that you feel like are missing? Okay, basically, a very short, just a few lines would be good enough. This is one way. This is really just my way to really encourage everyone to watch this tutorial. I know some of you already attended this tutorial session, which is great, right? That means all you need to do is to write a short review, a brief one. That's good enough. Okay, and again, this tutorial should help many of you, right? When you debug some of these lab assignments, right? This tutorial actually teach you how to use a waveform and such. Okay, and you get one. Yes, you get one extra by answering the bonus question, or you can get more than one if you provide the review and you get a bonus point through this and through answering these questions. Right? Not just one. But I imagine many of you, right, so may not be lucky enough, right, to be able to answer the bonus question during lectures. This is why we give you the second way. All right, and also I want to remind you that we have 3 lab assignments due. One today, this is pre-lab 3B, and another one tomorrow. Make sure that you check the PR's announcement. Nikita made 2 announcements, right? One is he actually posted the correct FSM for pre-lab 3A. Make sure that you check this solution. Make sure to compare your FSM against this solution, okay? Just in case there are some issues with your design. And also read his latest PR's post, because we noticed that some of you got your simulation right to work, is passing all the test cases, but it's actually failing to work on the actual FPGA device. So that's where you may have this timing violation. You may either have the invert latch, or you may have a very long critical path delay. That's where you need to look into your design and try to fix the timing issue. Okay. All right. Any more questions? Again, about this slip day, you can actually use it to an extra assignment, not just in the syllabus, right? So we limit you to 2 assignments with this extra one. You can either use it on one of those 2 assignments, or you can use it on the 3rd data assignment. Okay, hopefully many of you will be interested to watch this tutorial. I already have the link here. This is a link to the first part of the YouTube video. We have actually two parts, right? Both of them are linked on Piazza. Okay. All right. So before I talk microprocessor, let me quickly review what we covered last time, right? Last Thursday, we talked about memory, right? Memory technologies. Specifically, we talk about SRAM, right? And DRAM. What does S stand for? SRAM. Guys. Very good. Static. Okay. The reason it's called static is because in contrast, right, to DRAM, DRAM is dynamic RAM. With static RAM, we don't need to do the refresh, right? Because we are using these cross-coupled inverters, which are always powered. We don't need to refresh its content. In contrast, right, if you look at DRAM, we have this a single in the bit cell, right? We have a single transistor and a single capacitor. That capacitor may lose charges. That's where we have to refresh. So with that in mind, which one is more expensive in terms of area, SRAM or DRAM? DRAM? Let's focus on one specific bit cell. How many transistors do we have per bit cell in the SRAM? Let's be more concrete. Very good, right? That's called a 6T, right? We have a 6T bit cell. Let me try to advance the slide. Okay, first, with SRAM, it's usually on chip. It's usually sitting together with the CPU on the same chip. And SRAM gives us a faster access, right? Since we don't have to do this dynamic refresh. So that's where we get a much faster access. But the downside, there's a trade-off, right? The downside is we do have to pay more for more area and cost per bit because we have 6 transistors, right? 2 per inverter. And we also have 2 more transistors to connect to the bit lines. Okay, so with DRAM, this is typically off chip. And we only have 1 transistor, right? 1T is a 1T bit cell, which means this is a lot more compact, right? A lot more dense, a lot denser. And also the cost is lower per bit. Although the prices, this is actually slower, right, with DRAM. One thing is about this refresh. The other things, last time I talked about this, right? We also need to do this so-called multiplexing, right? We need to multiplex the row address and the column address because usually DRAM is sitting on a separate chip, right? Separate PCB board. That's where this pin count is a resource constraint, right? It's limited. If we do need to multiplex even the addressing part. So the addressing part is also slower. Okay, so this is a trade-off. And usually, so just want to give you guys some sense, right? Usually for SRAM, so the capacity of an SRAM module is usually in the order of a kilobytes. So this is a range, right? 2 megabytes, right? M means mega. Last time we talked about this, right? K means 2 to the 10, right? M means 2 to 20. For DRAM, most of you already know, right? This is usually in the order of gigabytes, right? This is 2 to the 3rd. Because indeed, we can pack a lot more, right, on a single chip. And also, over here, we are showing a sort of physical view of the DRAM, this n by n bit array. So what we can get from this bit array is per transaction, per read transaction or write transaction, we actually only access 1 bit. But we talk about this as so-called word, right, in the memory, in a random access memory. So with DRAM, to get 1 word, we actually need to access multiple bit array like this in parallel to get 1 word out. Okay, so this is not something that we talked about last time, because I intentionally gave you a very fast and also a very quick overview of these 2 main technologies. Like I mentioned last time, this is both of these are very rich topics. You can actually spend many more lectures, right, on either SRAM or DRAM. But the purpose of the last lecture is really meant to give you guys, a high-level overview of how this thing works and what are the high-level design trade-offs. Okay. Any more questions about SRAM and DRAM? Okay, if not, let's do analogy. Again, sort of imprecise analogy, just to give you guys some more intuition about what's the design trade-off involved. Okay, so let me try to draw a parallel between this memory technology and the buildings. Okay. Over here, we have this apartment building, right? And over here we have this sort of commercial or business building, right? Now, you want to draw analogy. So which one is SRAM? Which one is DRAM? The commercial building is the DRAM or the apartment building? DRAM is on the left. Right, very good, right? So the commercial one is, in my analogy, right, is DRAM. Okay. Think about this, right? In this building, we have many rooms, right, for storing things. It could be people and other stuff, right? And you can treat this room as a bus cell. If you look at this commercial building, indeed, each room is much more compact, right, than the room in the apartment building. Usually that's the case. Of course, they may have big rooms, but these big rooms might be divided into this so-called cubicle area, right? Cubicle, the cube cells. Okay, and this is more like SRAM. Okay. Make sense, right? Also, it's more expensive, right? Usually, for a bigger room, the brand is more expensive. How about a house? Is there an analogy? Can we draw an analogy here? What does the house correspond to? Excellent, very good. Okay, maybe D latch, right? Or DFF. Okay. So which one is faster to access? DFF or SRAM? Let's say we want to read from the DFF, or we want to write to DFF. Why? Why is DFF faster? Smaller? Yep, that's one reason. Anything else? Think about this SRAM, right? This DRAM. The reason I'm using this analogy is think about these buildings, right? When we want to go to one room, for this commercial building, we may need to take the elevator, right? For this apartment building, we may have to walk the stairs, right? Very good, right? So there's the addressing part, and there's this big decoder, right, in front of this cells, right? There's a cell array that makes things slower, and of course, there are other things, right, as well. Like for DRAM, you actually need to multiply the addresses, right? There's a refresh and all of that. Right? With DFF, it is right much easier to access. Right? Also DFS, right? For multi-bit DFF, it's called register. Right? Many of you already mentioned this thing, and we're going to be looking at register a lot today in this lecture. Okay, one more question: how large is a DFF roughly in terms of number of transistors? We just talk about per bit cell, right? This 1T DRAM, this 6T. How about latch? Let's talk about latch, D latch. How many transistors per D latch? Any guess? 2. How many transistors do we have per SR latch? In an SR latch, how many gates do we have? How many NAND gate or NOR gates do we have? SR latch. Let's just talk about SR latch first. Let's say this is SR latch. Yeah, 2 gates, right? Very good. Okay. Let's say we have a NAND gate, 2 input NAND gate, right? We have two input NAND gates. How many transistors do we have per NAND gate? Including both PMOS and NMOS. 4, right? Very good, 4. Okay, in case you already forget, right? So make sure you refresh your mind, right? Take a look at the CMOS lecture. Okay, for NAND gate, we have 4 transistors, okay, per 2 input NOR or 2 input NAND. Okay, hopefully this help you get some sense of how many transistors do we need for a latch, right? Although there are actually a lot of interesting and efficient implementation of a DFF. So usually for DFF or 1-bit register, we need to use like roughly 10 to the 20 transistor. Okay. There are some efficient way to build this DFF. That's actually also one of the reasons where we have the setup time and hold time constraint. Okay, I'm not going to get into detail. All right, hopefully these analogies are helpful. Okay, great. Okay, so with that, we pretty much conclude the part one, right? The first part of the course. If you look at the list of topics here, right? We have actually covered quite a bit of material. We talk about Boolean algebra, right? Conditional logic, sequential logic, Verilog, FSM, right? Time analysis, and SRAM DRAMs. Okay, so if you guys managed to follow me right up to this point, congratulations. You guys already have a very decent understanding, very solid understanding of some of the fundamentals of digital system. Okay, so these are the fundamentals that you guys need to know. And also you guys have learned quite a few very useful and important building blocks, right? Like muxes, decoder, right, counter, and such. And we are going to be using this building block, right, to build something a lot more interesting, right, and also more complex, more powerful, and more useful. And we're going to learn to build a digital computer, and we're going to start with a microprocessor. Okay. All right. And later on, we'll also talk about the memory system, how the microprocessor interact with the rest of the memory system. Actually, in this memory system, we're going to be using DRAM, we're going to be using SRAM, and of course, we also use registers. There will be a hierarchy in this memory system. And we'll briefly talk about how we take inputs and how we produce outputs. Okay. All right, so let's just start building this microprocessor. I've been showing this diagram to you guys, right, for quite a few times. We look at ALU, right, and we look at this RAM, data RAM briefly. So now let's try to make sense of the rest of the components on this diagram. Okay, so let's start with, let's come back to ALU. Let's talk about how we actually do the compute. I think we mentioned before, right, ALU is sort of the compute core of the microprocessor. Right? We can do different kind of operations on this ALU, right, like addition, subtraction, right, logic operation and such. We have this ALU, the ones that we have 2 data inputs, right, 2 operands, input operand, and 1 output, data out. Right, so this is the conventional logic. Let's say, for today's lecture, first, because for the microprocessor, right, we build this microprocessor to crunch numbers, right, to do compute. So let's say in today's lecture, I'm interested in doing an expression like this: b squared minus a squared plus 1. Okay, of course, you guys know that this translates to this, right? Okay, so this is the expression that we want to compute. So this is my driving example. All right. If you look at this, right, we actually need to grab, right? We need to find data, grab data like A, B, right? They need to be stored somewhere, and also the intermediate results, A plus B, B minus A, right? So those need to be stored somewhere. So that's where we need registers, right? We actually need more than 1 registers. Do you guys agree? At least we need a few, right? 3 or 4 at least, at the very least, just to compute this expression. We need A, right? To store A, we store B, and some of the intermediate results. That's where we need to use this so-called RF, or register file. Okay, this means register file, RF. This is basically a collection of registers, and each register has an index. Okay, meaning that we can actually address each one of this register in the RF, in the register file. This is where we save the intermediate results from our computes. Okay, so the way that our this basic processing cycle work is, at each cycle, we grab 2 data from the register file, from the RF, and then we send it to the ALU. We then send the result of the ALU back to one of the registers in the RF. Okay. Right. Again, so we read 2 data from 2 registers and perform some operation, then place the result back into this register. The reason this is called the basic processing cycle is because actually all these 3 steps can be done in 1 clock cycle. Right? Any questions so far? Okay, so this is sort of the backbone, the sort of the simplest view of our microprocessor. Essentially, each clock cycle, we grab 2 operands out and then do some operation and then write it back to this so-called RF. Now let's try to understand how exactly does this RF work, right? And what are the signals, right? What does this mean? Like LD, SA, and such. All right, first, RF, right, is basically a collection of registers. So for now, let's try to be generic, right? Assume that each register holds n bits. So usually this n is a power of 2, right? Usually in the modern day microprocessor, we have 32 or 64, right? So that's the n. But in our 2300 microprocessor, we usually should assume that this n is either 8 or 16. I think in the next lecture, we're going to assume that this is 16. Okay. And we have 2 to the k. Sorry, this is a typo. I'm going to fix this. This is 2 to the k, not 2k. Okay. 2 to the k. K is the number of bits in the address. Okay. So we have 2 to the k number of registers. And we have, for this register, this is the important thing that you guys need to remember. For the register, in our case, we have 2 read ports. Okay. We have 2 read ports, meaning that this register file can output 2 data, and we have 1 write port. Okay. For 2 read ports, we have data A, data B, and we can write 1 value back to the register file. We can do this 3 at the same time. Okay. We have 3 concurrent ports, meaning that we can grab 2 data out, and then we can write 1 data in at the same time, in the same cycle. 2 read ports on 1 write port. The write port is called D in. Since we have 3 ports, right, and also we have a collection of registers, and also each one of these registers has an index. That's where we also have 3 addresses. Right? So that's where we have the so-called control inputs. For data A, that is the first read port, we have something called SA, or source address A. This is basically the address for indexing the register for data A. And similarly, we have SB, SB for addressing the register for data B. And we have destination address, okay, for this guy, for the write port, for D, DR. And we have a strobe, a single bit strobe called LD. LD indicates, LD is basically write enable. LD is a write enable. If LD is 1, it means that we are actually writing something back to the register file. We are changing the state of the register file. Otherwise, if LD is 0, we are not writing anything. Okay, all right. So this is somewhat abstract, right? Let's try to look inside, and let's try to understand how exactly this thing is built. All right. First, let's look at a very simple example with just 4 registers. We have 4, okay, in the RF. So how many bits do we need per address? Just 2, right? 2 bits. See here, we have 3 addresses, right? Each one has 2 bits. SA1, SA0, right? SB1, SB0, and here, DR. So these are the addresses. Okay. And this is the read port, right? So we want to read out 2 values, data A and data B. What do we do, right? So we may need to select from any one of these 4 registers. That's where we need muxes on each port, right? over here we have this 4 to 1 mux for each write port. And we use SA and SD as the selection signal for the mux. After that, all we need to do is actually we can choose to read for both data A and data B, we can choose to read from the same register. So that's where each register actually connect to both output ports or read ports. That's where we have fan out like this, right? And same for reg 1, reg 2, and reg 3. Okay, just want to be clear, just want to make sure that you guys understand, right, what's going on. If SA is, let's say, 1, 0, which register do we read out from data A? Just want to make sure that you guys are following me. Very good. Reg 2. Basically, SA is just telling us the index of the register that we are reading. Same for SB. Okay, good. So how about this guys? The write. We also have 2-bit address, right? For DR. DR means destination register. The address for the destination register. Okay. So how do we address these things? This is where we need a decoder, right? Similar to the, the SRAM and DRAM. So here we have a smaller decoder, right? 2 to 4 decoder. Reason enable. So here we have enable. This enable signal is connected to LD. LD means load, right? Load LD is write enable. If LD is 1, we are writing. Otherwise, we are not. So all we need to do is we connect the output lines of this decoder to the enable signal. This is something sort of new, right? With a DFF, usually we only have a D input and a clock input, right? So over here we have some enable signals here connected to blue lines. So later on, the convention here is that the blue lines are the control signals. The black lines are the data signals. Okay. If enable is 0 for the register, that's where we have, that's where we don't really write to the register. The register is disabled. We don't take new D. Okay, so Alma's asking, is this example reading or writing? Good question. Like I mentioned, right, we actually have 3 concurrent ports. We have 2 reads, 2 read ports, and 1 write port. We can actually do both read and write at the same cycle. But if LD is 0, then we are only doing read, not write. Does that answer your question?
Yeah, I guess my question was more like, so if the enable is 0, like if LD is 0, all the registers have their enable 0, can you still read from that or no?
Oh, good question. All right, now I get your question. Yes, you can still read from it. The enable is really just the write enable. This is the write WE. Okay, we can still read.
That makes sense, thanks.
All right, but just want to remind you guys, right, about program 1, we actually already built some register like this with the enable in the last question. I'm not sure whether you guys still remember. There's one easy way to build a register with enable. Do you guys remember? What do we do? I think that's Q7, right? We asked you guys about one register, whether we can code or not, right? Basically, hold means that we are not writing. So in that example, in that question, all we are doing is we just turn off the clock. That's it, right? We gate the clock. Something like this, right? This is a clock signal. All we are doing is we gate the clock. We just put a 0 here. This is one way to build an enable for a register. Hopefully this makes sense, right? Because DFF is an edge sensitive device. All we need to do is to gate the clock to turn off the edge. All right, any questions so far about this RF register file? Okay. LD is an important signal. Okay, Somebody is asking, what do the ends on the line mean? All right, good question. So this is basically a end bit signal. Okay, we haven't defined n yet. Usually, like I mentioned, n is for modern processor is 32 or 64. But in our case, we usually assume that this is a simpler, right? Either 8-bit or 16 bits. This is based on multi-bit line. This is a bus, right? And we use this slash, right, to indicate the bus. That's the notation. Okay, so now that we have this register file, right? We have the ALU. Okay, we need to tell the processor, right? This is a basic processing unit to let it know what kind of operation we want to do. I want to remind you guys again. So what we want to do is a plus b, right, times b minus a plus 1. This expression that we want to compute. So let's try to first compute this one, a plus b. There's one more question. Okay, which? Okay, let's come back to the RF. Right, from the pre-example, which lines are the right lines? The right line is the D in. Right, this is this guy. D in. This is the data line that we write to. Right, D in is connected to this D inputs right, here. Okay. All right. Oh, where does it get written? Oh, good question. But since we have a decoder here, right? Only one of the lines is hot. If LD is 1, right? Let's say here, I should have clarified, right? If DR0 is 1, D1, DR1 is 1, which register do we write to? Guys, this is a decoder. This is a question for the class. And this is a 1. Very good. Reg 3. Okay. That's how we use the decoder for, right? Remember in SRAM, DRAM, we also have something like this, right? Where we basically activate the word line using decoder. Very similar technique over here. Make sense? Okay. All right, coming back to this one, we want to do addition. So let's say our processor can actually understand some descripted way to describe a compute. This is a so-called instruction. Okay, over here I'm showing a very simple form. Right, this is where we tell the processor that we want to do this addition. So what we want to do is we first in this format we first indicate the operation, which is the add. Then we indicate the source registers. We have 2, right? Over here, we are adding R1 and R2, and we are writing to the destination register. Remember here, the first one in this case, right, is destination. The 2 on the right, right? These are the source registers. I'm going to give you the more concrete definition, more detailed definition of this instruction format in the next lecture. But this is basically how we write so-called instruction. That's how we tell the microprocessor to do certain compute using a human readable form. Okay. All right. Let me finish this one first. Right? I think there are more questions about RF, right? Which is good. So this is basically the pseudocode, right? What we exactly are doing here is we are trying to add R1 and R2, right, and write it to R0. So basically over here, we can assume that B is stored in R2, right? A is stored in R1. Okay, so this is the instruction that we want to perform. And there's one more question about RF. The question is, so do we have to write all registers to already in RF, or you cannot keep some values and change others? First of all, right? Okay, since we have a decoder, coming back here, we have a decoder. Decoder is 1 hot, right? Decoder is 1 hot without enable. So only one of the blue lines will be hot, right? At any given cycle, if LD is 1, we can only write to one of the registers, right? Agree? And if LD is 0, so this is decoder with enable. This is something that, this is actually a decoder, right? With enable. is something that we have learned, right, in an earlier lecture. So if the enable of the decoder is 0, all the blue lines will be code or zeros. So that's where we don't need to write to any of the registers. Is it clear now? All right, good. Yeah, so these are good questions. So again, it's really important to understand SA, SB, DR, and LD, right? The function of the RF. All right, so this is the addition, right? So let's first do addition. So we basically tell the ALU, we are not going to use binary code here. OP code, we just say add, okay, over here. And then we are gonna provide these values, right? So we wanna read from R1, right, R2, so this is read R1, R2, and we wanna write to R0, right? DR is R0. And we say that we do wanna write. So that's where we put, we set LD to be 1. So these are the control signals that we have to supply to the RF. Once we have this, then we can get the data out, right? And from the RF, and then we can do the compute using ALU, and then rewrite it back to the RF. This is a basic processing cycle. Okay. Any questions over here? If not, let's look at the waveform. Okay. This is the clock, right? We first provide the operation at the same time. We provide, this hexagon, right? Again, we are using hexagon, indicate a stable signal. This can be more than 1 bit. I'm just using a simplified waveform here. Okay. And we have SA, right? We provide the source register addresses, SA and SB, and we get data out. Okay. So one thing I want to mention here is that once we provide SA and SB, we actually don't need to wait until the next clock edge, right, before this data A and data B, right, to show up, because this is recombinational, right? We are not writing to the register file, we're reading from the register file. So that's why we don't have to wait until the next clock edge to see data A and data B. And we get R1 plus R2, okay? And we also assert, right, LD, this is where we assert LD, meaning that we want to write to the register file. Okay, and we also provide the destination address. This is R0, basically. We write these values into the register file. Over here, this guy really means that the value in R1. Okay. The square bracket R1, so I'm using this notation to indicate the value stored in R1. It's not clear. Okay. Right, so this is waveform. We just finished addition, right? One more time, we want to do this, right? Okay, let's try to complete this. Right, Manda's asking also a good question, right? How do we get operation to the LU? There's actually some actual control logic that I'm going to talk about later on in this lecture. For now, let's just pretend that all of this magically show up. Okay, let's just focus on the so-called data path, right, where we look at the functional unit and the storage. Let's just to pretend that these things are just applied by some magical, right, control unit. All right, and we want to do, right, so we just finished this one. Let's do subtraction. To do subtraction, it's very similar. Actually, not too interesting. All we need to do is, we put stop here, right? In the next clock cycle, after the clock edge, right? So this is the edge. We supply the operation, the opcode stop, and we set the right addresses for the source registers. In this case, we are doing this, right? What we're doing is R3 is assigned with R2 minus R1. Okay, this is basically B and A, right, in my example. And we get the data, and we get the difference, right, between this the values in the registers. And this is the stroke. LD stays high. We do want LD to be high, right? Because we are writing that to R3. This is basic R3. All right, any questions so far? This is the basic operations, right? Just add and sub. Okay. And one more time, we are using this, right? The R2, right? In the square bracket means that we have, we are using the value stored in the register R2. Okay. So now that we have, right, in my example, we have A plus B, right? I keep writing this, right? This is done, this is done. We are going to look at how to do a multiply using just add and shift later on, most likely in the next lecture. But now let's also complete. Let's pretend that we already have the product in R3. Let's do this. Let's do an operation that adds a constant. Okay. Right, and this is the instruction. We have a variant of this addition. We have something add I. Add I means we are adding an immediate value. I'm going to explain what exactly is I or immediate means, okay, pretty soon. And this is the instruction format, right? We want to add 1 to R3. That's it. So this is what we want to do. Anyone? Any guesses? Right? Why this kind of pattern shows up a lot in your software program? Any guesses? Why? Not adding value from a register. Yes, we are not adding value from a register here. We are adding a constant increment. Very good. Okay, can you guys write on the? Do you guys? You probably have seen this, right? So when we increment the loop counter, we do this a lot, right? Or I plus plus. Okay, so that's why we actually want to provide special instruction to support this kind of operation. All right, and this is right, a constant. We are one of the operands is a constant, and this constant is usually called immediate value because this constant is not stored in the register. It's actually encoded as part of the instruction over here. Next lecture, we are going to talk about how we encode this constant in the instruction. So that's where it's called IMM. Okay, it's immediate. It's immediately available after we parse, after we decode the instruction. And we usually have the sign extended SE here. So this SE. This one is a sign extend. Okay. We actually talk about this right in one of the earlier lectures, I think last week, when we talk about the binary arithmetic. This is where when we have to add up something, right? So with different sizes or different bit widths, that's where one of the operands needs to be sign extended in the 2's complement format. So assuming that for now, all of this are stored in the 2C format. Okay. Because usually we can only store short and small constant in the instruction. This is something that's going to be very clear in the next lecture. That's where we need a sign extension. Okay. But coming back to the data pass, can you guys tell me, like, to complete this instruction, right? You want to add 1, increment R3 by 1. What should be these control signals? Of course, we assume that this one is a 1, right? The immediate IMM is assigned with a 1. What is this? This is the control signal for the mux, right? Over here now, the ALU can actually take either the data B or this immediate value. What should be MB? MB means the mux for B input. This should be 1, right? We're gonna take the immediate value. Very good. How about LD? Let's look at the RF signals. LD 0, 1. Are we writing or not with this instruction? 1. Very good. We are writing to R3, right? We want to update R3. So that's where LD means we load something into the register file, into RF. This is a 1. How about SA? SA? What's SA? We want R3 here, right? We got 1 here. 1, 1. Very good. SA is 1, 1. let's look at DR. DR is also 1, 1, right? Because we are writing to R3. How about SB? This is the more interesting case. What's SB? Very good, don't care. Because we are not using this, right? This is don't care. Very good, don't care. Make sense? Good. All right. Okay, and this is just a sign extension, right? No. If you want to send the 4 bits to 8 bits, we just append the sign bit on the left. Okay, all right. So one more question. Where does MB come from? These are the control signals that for now, we just assume that they just magically show up at the right time. Okay, I'm gonna talk about this. I'm gonna talk about control units soon.